Okay. What would happen if you were to gather a mole, the unit of measurement, of moles, the small furry critter, in one place? If you gathered them in one place, well, things get a bit gruesome. Gruesome. What does gruesome mean? Gross, nasty. Yes. First, some definitions. A mole is a unit. It's not a typical unit, though. It's really just a number, like dozen or billion. If you have a mole of something, it means you have this many of them, usually written 6.022 times 10 to the 23rd. It's such a big number because it's used for counting numbers of molecules, which there are a lot of. There are too many molecules. A figure with a hand overflowing with molecules. 1 mole is close to the number of atoms in a gram of hydrogen. It's also, by chance, a decent ballpark guess for the number of grains of sand on Earth. So if you want to measure the sand castle, it's going to be less than a mole of grains of sand. Unless you use all of the sand on Earth, including the sandstone, and grind it into grains. Now, a mole is also a type of burrowing mammal. There are a handful of types of moles. Some of them are truly horrifying. The star-nosed mole. Anybody want to see the star-nosed mole? There it is. There's the star-nosed mole. That's its face. Okay. So what would a mole of moles, or 6.022 times 10 to the 23rd animals, look like? First, let's start with wild ballpark approximations. This is an example of what might go through my head before I even pick up the calculator, when I'm just trying to get a sense of the quantities, the numbers. Kind of calculation where 10 and 1 and 0.1 are all close enough we can consider them equal. Don't do this in math class. Okay, don't say 10 and 0.1 are equal. But in science class, it works sometimes. So I can pick up a mole and throw it.
Why would I pick it up?
Not saying you should or would, but you can. It's physically possible. Well, again, you may not. Okay. No, you can. You have the muscle power to do it. That's what can means. Ah, okay. All right, there you go. Anything I can throw weighs 1 pound. Again, that's not true, but let's pretend. 1 pound is 1 kilogram. Again, it's not true, but it's close enough for approximations. The number looks about twice as long as a trillion, which means it's about a trillion trillion. I happen to remember a trillion kilograms is how much a planet weighs. Okay, 1 mole, a trillion. If anyone asks, I did not tell you it was okay to do math like this. All right. Morning, Emirates. Please pull out your headphones. Thank you. All right. Now, that's enough to tell us we're talking about a pile of moles on the scale of planets. So if I have a mole of moles, it's going to be similar to a planet. It's a pretty rough estimate, though, since it could be off by a factor of thousands in either direction. So let's get some better numbers. An eastern mole, so not the star-nosed mole we saw earlier, weighs about 75 grams, which means a mole of moles weighs, actually, 4.52 times 10 to the 22nd kilograms. That's a little over half the mass of our moon. So much smaller than Earth, but still really, really big. Mammals are largely water. A kilogram of water takes up a liter of volume, so if the moles weigh that many kilograms, they take up about that many liters of volume. You might notice we're ignoring the pockets of space between the moles, and in a moment you'll see why. The cubed root of 4.52 times 10 to the 22nd liters is 3,562 kilometers, which means we're talking about a sphere with a radius of 2,210 kilometers, or a cube, 2213 miles on each edge. That's a neat coincidence I've never noticed before. A cubic mile happens to be almost exactly 4/3 pi cubic kilometers. So a sphere with a radius of x kilometers is the same volume as a cube that's x miles on each side. Just one of the oddities of math. Now, if those moles were released onto the Earth's surface, they'd fill it up the Earth's surface that is, up to 80 kilometers deep, not just the solid parts, okay? Can you put the phone away, please? 80 kilometers deep, just about to the former edge of space, okay? So here's the mantle, the crust, the moles. Moles are thicker than the crust. Then the air gets pushed up, and there's the International Space Station. Now, this smothering ocean of high-pressure meat would wipe out most life on the planet, which could, to Reddit's horror, threaten the integrity of the DNS system. So doing this on Earth is definitely not an option. Instead, let's gather the moles in interplanetary space. Gravitational attraction would pull them into a sphere. Meat doesn't compress very well, so it would only undergo a little bit of gravitational contraction, and we'd end up with a mole planet a bit larger than the moon. Again, even though the mass is less than the moon, water is not as dense as rock, usually. So you don't need as much volume on the moon as you have with the moles. Now, the moles would have a surface gravity about 1/16 as strong as Earth's, similar to the surface gravity of Pluto. It would be uniformly lukewarm at the beginning, probably a bit over room temperature. Gravitational contraction would heat the deep interior by a handful of degrees, but this is where it gets weird. The mole planet is now a giant sphere of meat. It has a lot of latent energy. There are enough calories in the mole planet to support the Earth's current population for 30 billion years. 30 billion years, which is about how long it would take you to count up to one mole if you counted a million numbers per second. You know, 1, 2, 3, 4, 5, 6. Count up to a million every second. It'll take you 20 billion years. Mole is a really large number. Exactly. The whole universe would be dead. Normally, when organic matter decomposes, it releases much of that energy as heat. But throughout the majority of the planet's interior, the pressure is over 100 megapascals, which 100 kilopascals is our normal air pressure. So this is a huge amount of pressure. That's enough to kill all bacteria and sterilize the mole remains, leaving no microorganisms to break down the mole tissues. But closer to the surface, where the pressure is lower, there's another obstacle to decomposition. The interior of a mole planet is low in oxygen. And so without oxygen, the usual decomposition also doesn't happen. The only bacteria that can break down the moles are those that don't require oxygen, which there are a lot of bacteria that are anaerobic. Now, while this is inefficient, this anaerobic decomposition can unlock quite a bit of heat. If continued unchecked, it would heat the planet to a boil. Again, that's not in the core of the mole planet. That's closer to the surface. However, the decomposition is self-limiting. Few bacteria can survive at temperatures above about 60 degrees Celsius, or about 130 Fahrenheit. Okay. So as the temperature goes up, the bacteria die off. Decomposition slows. So all throughout the planet, the mole bodies gradually break down into kerogen, which is a mush of organic matter, bless you, which would, if the planet were hotter, eventually form oil, just like we had oil form underground here on Earth from the dinosaurs and whatnot. Now, the outer surface of the planet radiates heat into space and freezes because it's space. Because the moles form a literal fur coat, when it's frozen, it insulates the interior of the planet, slows the loss of heat to space, but the flow of the heat in the liquid interior is dominated by convection. Plumes of hot meat and bubbles of trapped gases like methane, along with the air from the lungs of the deceased moles, periodically rise through the mole crust and erupt volcanically from the surface, a geyser of death blasting mole bodies free of the planet. Eventually, after centuries or millennia of turmoil, the planet calms and cools enough it begins to freeze all the way through. The deep interior is under such high pressure that as it cools, the water crystallizes out into exotic forms of ice such as Ice 3 and Ice 5, and eventually into Ice 2 and Ice 9. I'm not going to click that, but do you guys know what Ice 9 is in other contexts? Okay. It's a funny story, but it's too much of a rabbit trail. All told, this is a pretty bleak picture. So let's try an alternate approach. I don't have any reliable numbers for global mole population, but we'll take a shot in the dark and estimate that there are at least a few dozen mice, rats, voles, and other mammals for every human. Okay? So there might be a billion habitable planets in our galaxy. If we colonized all those planets, we'd certainly bring mice and rats with us. We did it when we went to Australia. Surely we'll do it. It's part of the food web. We need it. If just 1 in 100 of those planets were populated with small mammals in numbers similar to Earth's, then after a few million years, which is not long in evolutionary time, the total number which have ever lived would surpass Avogadro's number. So if you want a mole of moles, build a spaceship. So Elon Musk is working on that right now. So there you have it. A mole of moles. Gives you a sense of what a mole is as well, in the sense of the number. Okay, it's a really, really big number. And so now back to our regularly scheduled lecture. How to convert between the number of particles and moles. Okay, so let's say you want to know how many atoms are in a mole of a compound. Well, you know what a mole by definition is. But you also need to know how many atoms are in a particle of the compound. So you're going to have to do some multiplication here. So let's see here. We have a dozen cups here with marbles. Each of the cups has 6 marbles. I mean, they have different designs and whatnot, but there are 6 marbles in there. So 6 times 12 is 72. And same thing, a mole of molecules has more than a mole of atoms, by definition. In CO2, you have 1 carbon and 2 oxygens. So there are 3 atoms. So a mole of carbon dioxide has 3 times Avogadro's number of atoms. Okay, so we're talking about 1.8 times 10 to the 24th, which is more than a trillion. So if you want to know the number of atoms, first you have to know the number of representative particles. Okay, so if it is molecules or formula units, we'll just say molecules for short, even though like sodium chloride is not a molecule. So it's that many divided by a mole. All right, now the size of a mole. There's a much less scary looking mole, okay? This one will cleanse the mind of the memory of the other mole. Look at this mole. This is a nice, cute mole.
Yeah, medicine one cute little hole.
There you go. Right. Like a little dirt swimmer. No, that's getting personal. All right. Anyway, so let's say an average animal mole is this long and has a mass of 145 grams. Oh, I was sharing. I thought I was, and then I switched over to this slideshow. Everything I said earlier was just words anyway. There wasn't any diagrams, but here's a nice mole. Okay, so the mole of moles is going to be this many kilograms, which kind of lines up with what XKCD was saying. So it would be 60 times the combined mass of Earth's oceans. If it spread over the entire surface of all Earth, you would have 8 million animals thick. In the XKCD article, they talked about kilometers, like I think it was 60 kilometers, or was it 80 kilometers? I forget which one. Way, way taller than Mount Everest. And if you lined all those up to end, we would reach from Earth to the nearest star 2 million times. 2 million times. So imagine 2 million rows, okay, so like 1,000 by 2,000 rectangle of rows of moles from Earth all the way to Alpha Centauri. It's just a ridiculous thing you can't really picture. All right, so enough of those animal moles. Now, if we have the number of atoms, okay, how many atoms are in propane? Well, there are 2 elements, okay, 2 elements. What are these 2 elements? All right, hydrogen and carbon, right? Carbon and hydrogen. And so, but how many atoms are there? $11, right? Just add up 3 and 8, right? There's no multiplying here; it's just addition. So again, we want to go from the moles, which are given to us, 2.12, to the molecules, all right, which is Avogadro's number, and then the number of atoms is 11 per molecule, per representative unit. And so, how many atoms? Got to multiply those all together, and straighten this out. There we go. So it looks right. All right, so you have this, again, a mole of molecules per mole of that. Got to make sure you cancel these things at 11 atoms per molecule. So up here you've got molecules, down here you've got molecules. Molecules will cancel out. Molecules cancels out molecules. Moles cancels out moles. I don't know why I can't get the formatting right here. And so you'd have what you want, which is atoms. And so you have 1.4 times 10 to the 23rd atoms in 2.1 moles of, that can't be right. Must be times 10 to the 25th. Yeah, I couldn't have gotten smaller. Maybe it's 24, no? All right, somebody take 2 times 6 times 11. Yeah. Okay, 113, all right.
132. I did that in my head, that's probably not right.
132, 132. Okay.
Like, oh, I'm
all right, so yeah, 132, that's going to be 1.32 times 10 to the second. So they forgot to increase their power here from 23 to 25. Sheesh. This is why I always fix these things before I post them. All right, now there are 11 atoms again, and our answer per sig figs, we had 3 all the way along, and now you might say, but Mr. Bowden, 1 and 1 and 11, those aren't 3 significant figures. So those are exact numbers. By definition, it's exactly 11, 11.0000 atoms in methane, or excuse me, propane, or else it's not propane. Okay, so it may not show things, but exact numbers that are defined don't need to have a certain number of visible digits. Measured things like the measured moles of this, do need to have, you do need to count those digits, and then you're limited in your answer to that. You want to claim as much precision as possible without claiming too much precision. Okay, so mole is similar to a dozen because they're just weird words for certain numbers. Okay, they count things. All right, molar mass. We're shifting gears here again. Everything on the periodic table has a mass number below it. So many AMUs, okay, atomic mass units. And if you take a look at the periodic table, generally speaking, the more atomic numbers you have, the more protons you have, then you have as many more neutrons, and so the mass always goes up. But once in a while, like from argon to potassium, the mass actually kind of goes down, and I think also from cobalt to nickel, just because of the weirdness of isotopes and stuff. So once in a while, there's an exception, but generally, it goes up. The mass goes up as you go along the periodic table. So those are atomic mass units. So but now we're getting into molecules and that sort of thing. And so we're going to want a molar mass. So the beautiful thing is that it's the same number. You just change the unit. So instead of it being 12.011 atomic mass units for 1 atom of carbon, it's going to be 12.011 grams for every mole. Same number. It's just changing the unit. So again, atomic mass units, and that's what we did there. Again, I'm not going to go into all the detail here on this, but again, it's 12 to 1. But we use grams, not kilograms, grams. And so 12.0 grams for carbon is the molar mass, and it's 1.0 for hydrogen. Now, if you look at hydrogen, you'll see that that's not the whole story for hydrogen. There are more digits available. Same thing for carbon, but they round to that. You could say hydrogen is 1.01, but 1.01 and 1.0 do not disagree. It's just that one is more precise than the other. But we don't need that kind of precision right now. Okay, so whether we say 1.0 or 1.01, it's actually saying the same thing. Just a matter of precision. They're both equally accurate. So I'm going to leave it as 1.0.
We jumped around in this area.
You don't have to use the full number that's up on the periodic table or in the periodic table in your book, because sometimes, like for sodium, for whatever reason, they like to go out to like 10 digits just because they can, and they've actually accurately measured that. But you can just kind of go to the first, maybe the second decimal place, and you're good. Okay. All right. So carbon, sulfur, and iron. So if you have 1 mole of carbon, like pure charcoal, then it'll be 12 grams. If you have 1 mole of sulfur, it's 32.1 grams. And if you have 1 mole of iron, it's 12. Oh, that's not right. Seriously? Now it's, what is it, 53? What's the number up there for iron? Jeez. Is that right? Yeah. 53.0 or 53.8 or? Yeah, me neither. Pardon me. So iron, yeah, 55.8, sorry. Okay. 55. Sorry. I should have that memorized, but I'm a little rusty. Yeah, I should. Something as simple as iron. All right, come on, Savis. You're just really being lazy here. Oops, not 565 either. All right, 55.8 grams. All right. So now you'll notice that the volume kind of doesn't matter here. The iron is actually takes up less volume than the sulfur does. But the sulfur is lighter. And that's because the iron is more dense. It has a higher density. So mass and volume are not the same thing. That's the whole point of density, in fact, is mass divided by volume, you get density. And things that are towards the middle of the periodic table are more dense than things that are at the edge, towards the edges. So like Ficoni, cousin, those 5 elements from iron, cobalt, nickel, copper, and zinc, very common metals. Those are very, very dense. You go down from them, silver, gold, platinum, those are very, very dense. My ring is made of platinum and palladium, which is right above it. It's very dense, okay? For its volume, it's heavy. But you go to the sides, and if you had potassium or you had bromine, it wouldn't be very heavy. It wouldn't feel very heavy. Mercury is very, very dense and heavy. Lead is also pretty dense and heavy. So again, towards the middle, more dense. You go towards the edges like titanium and calcium, those are lighter, which is great, because we have a lot of calcium in our bones. If our bones were heavier, then it'd be harder to move us around. So yay, calcium phosphate, our bone stuff. Okay, so how many atoms are in a molar mass? Well, same thing as just a mole again. So the definition of the mole is 12 grams of carbon-12, not just 12 grams of carbon, but the particular isotope carbon-12. So if you just grab a bunch of coal and pretend it's pure carbon, that won't be quite right. You've got to take away the carbon-14. You've got to take away the carbon-13. Just the pure carbon-12. So that is the definition. Oops. So molar mass of magnesium, 24.3. Now I don't trust this anymore. Okay, 24.3. All right. And it has, that mass of 24.3 grams. 1 mole has that mass. So let's see here. I'm going to change this up here just a little bit again. Grams per mole is the molar mass of this, and 24.3 grams per mole is the molar mass of that. So 12 grams of carbon is 1 mole of carbon atoms. Well, carbon-12. All right, sorry, small edits. And the molar mass is the mass of 1 mole of atoms of any element. And it's going to be grams per mole. Okay. Let's see if I can search this too. There we go. Okay, so I have this compound here, sulfur trioxide, very common, especially when you do burn coal. It goes up in the air, reacts with the water in the air to make sulfuric acid, H2SO4. And that's a problem because that kills a lot of things. So you've got a sulfur and 3 oxygen atoms. So you can calculate the mass of a molecule by adding the atomic masses up. And you want to use the average atomic mass because that is generally what you have. You're not worried about one isotope. So the average atomic mass is 32.1, then 3 times 16.0. And then you add those all together. So 1 molar mass, 1 sulfur trioxide is 80.1. 80.1 atomic mass units. Then the mole has 80.1 grams. So that's the mass of 6.02 times 10 to the 23rd molecules of sulfur trioxide. Okay? So again, it's going to be the same number. It's always the same number. It's just a matter of is it AMU or is it grams per mole? Grams per mole. All right. So, and then with grams, add the masses. So either way, whether you think of it as grams or AMUs, either way, you're going to be using the same numbers. Okay? Same exact numbers from the periodic table, from the bottom of each thing. So, a mole of water is 18 grams. A mole of sugar, not your typical sucrose, but the half of sucrose that is used by your brain, which is glucose. If you have 6 times 12, what's the number there? What's 6 times 12? 72, right. And 1 times 12? 12, right. Add those two together, you get 84. And then 6 times 16? 96. So 96 and 84 adds up to 180. All right, so it's 180 grams for 1 mole of glucose. Again, it's the same number of particles. It's the same ridiculously large, trillion times a trillion number of particles. It's just that it's, you know, glucose is a lot bigger, and so it's going to take up more space, and it's also much more massive. It's 10 times as massive. It doesn't quite take up 10 times the volume, though. All right. And then, I'm not going to pretend to pronounce that. Oh, well, no, I will. I'll pretend. Para-dichlorobenzene. No, that wasn't that hard. All right, para-dichlorobenzene. So we've got 2 chlorines here, and we've got benzene, which is 6 carbons in a ring, and the other things on it are 4 hydrogens. So if we have, again, 72 plus 4 is 76, and 35.5? Yeah, 35.5 for chlorine, so 71. 71 and 76, yep, makes 147. All right. So I just always have to check these, you know, now that my trust has kind of been lost. And you'll notice they kind of look like butterflies or maybe ladybugs flying there. Maybe just my imagination. The chlorine being the big shell wings or something. I don't know, do you see that? Maybe I've had too much coffee this morning. All right. Para, by the way, means that they're opposite from each other. All right. So when we have hydrogen peroxide, we can have it break apart, and that can launch a rocket. You can make your backyard rockets just with a few key ingredients, one of them being one of those brown bottles of hydrogen peroxide. So cheap, yes? That is a great question. What is going on with the rocket that China launched? Okay, so China is making a space station because there is an international space station, but it's mostly controlled, let's be honest, by the US and Russia. Although, you know, sometimes it seems like China is on Russia's side. China also doesn't want to be on any one particular person's side, and so they also want to be kind of more independent. So they're making their own space station. Well, to do that, you have to throw the space station up into space, and then whatever did that throwing, the rocket, usually, whether it's Europe or Russia or America, usually when they send these things up, they plan ahead for what happens to the rocket. For instance, Elon Musk actually has his rockets re-land vertically, standing up, so they can be used over and over and over again. Well, they didn't plan ahead. The Chinese didn't. What they were focused on was the space station. The whole point is the space station, not so much the thing that got it there. And so while that part of the space station is up there, fine, completely fine. The thing that pushed it up there is now it's on an orbit that kind of gets close to the Earth and then far from the Earth and close to the Earth. And the thing with a wobbly orbit like that is that eventually it grazes against the upper atmosphere enough to slow it down. And the slower you go, then the less that you miss the Earth. The whole point of orbits is you are constantly falling towards the Earth, but you're moving sideways so fast you keep missing it. Okay, that's what the moon does going around the Earth. That's what space station, all the satellites do, GPS that you use on your phone. They all are constantly being pulled by the Earth. It's just that by the time that they hit where the Earth was, they moved to the side so much. Well, this rocket isn't doing that. This rocket is not missing the Earth too much. And so I think the projection I saw would be that tomorrow, somewhere between New Zealand and Newfoundland, which is a long ways on a globe. I don't have a globe in here. Somewhere in the easternish Pacific, it's going to crash. And it's, it's somebody compared it to like a small plane, debris spread out over several miles. Probably won't hurt anybody. We put more trash than that into the Pacific Ocean every day. So it's not like it's that big of a deal trash-wise. It's just the thought of not really caring. That's what concerns a lot of people. We'll just throw it up and we don't really care what happens to the rocket after that. It's not a big deal, So that's my summary of that. Okay. But yeah, so with the you can, and Elon Musk has proven this, you can use rockets that you can control and re-land, at least a large percentage of the time successfully. Some people don't care. Some people just want to put their things into space. All right. So you can have a reaction again with hydrogen peroxide and make your own rocket. It will not get up to space. The amount of fuel you need to put something into space is incredibly large, but you can make it go up out of sight. And you can even have a drone hovering nearby to watch the rocket go up. But anyway, so what is the molar mass of hydrogen peroxide? So, like, how much grams per mole? So, we know what the formula is. It was given to us, H2O2. We know that 1.0 or 1.01 grams of hydrogen goes in there. And this is why it really doesn't matter too much whether you have 1.0 or 1.01. When you add these together, that last digit goes away anyway. All right, so you add them all together. And so you're going to have, or sorry, you don't add first. I would have added first. That's all right. There we go. Nope, still not quite yet. There we go. So 2 moles of hydrogen times 1 mole of hydrogen, they cross out, grams per mole. You get 2 grams of hydrogen in there, 16 grams. Okay, so this is, I just look at the periodic table and I see grams per mole. I know it's supposed to tell me atomic mass units, but this is like an extra step. Oh well. Does this make sense to you? No, it doesn't. There we go. Yeah, 2 times 16 is 32. All right. All right, so 2 plus 32 is 34. 34 grams per mole is the answer. So, or you could take what you know, which is 18 grams per mole of water, and then just add another 16, because that's the difference between water and hydrogen peroxide. All right, so does it make sense? Yeah, it's about twice that. So there you go. All right. Molar mass is to moles of a substance, as atomic molecular mass is to atomic mass. All right. So moles, atoms, they're again, moles is just a number. A dozen eggs is just like 12 eggs. That's what it's saying. All right, and that ends our section 1 there, section 1. All right. Later, I will post some skill sheets. You haven't had those in a while. Post some skill sheets for section 1. Now that we're done with section 1, and you'll answer some questions about those. And you'll have till the end of the school day on Monday, so I don't want to clog up your weekend. However, if you do want to do them at some point, then you're free to do them over the weekend. But I'm not going to post them right now. The last 10 minutes, there are still a lot of things, a lot of holes on the gradebook I see for everybody that you can be working on. Let's see. Bye-bye. Is time to move on. Oh, good. I'll take a look at that Jamboard later. Looks like SAT numbers came back. Did you win? You can win money with the